Let's talk about the architecture of a Kubernetes cluster, showing how the control plane, referred to here as the Kubernetes Master, interacts with the worker nodes. So let's dive into each part in detail. First, let's talk about the client interaction using kubectl, APIs, and dashboard. And here we have a user interacting with the Kubernetes cluster using these tools. So kubectl is the command line interface used to manage Kubernetes resources. So this involves creating, updating, deleting, and querying the state of resources like pods, deployments, services, etc. APIs, this refers to Kubernetes exposing a RESTful API, which can be used to programmatically interact with the cluster. And this is the same API that kubectl interacts with under the hood. The dashboard is a web-based user interface for managing and monitoring the cluster visually, and it provides insights into the resources running in the cluster, making it easier for users who prefer a UI over a CLI. And the commands issued from these tools are sent to the Kube API Server in the master node to manage the cluster's desired state. And in the middle section here, we have the Kubernetes Master, also known as the control plane. And this represents the brains of the Kubernetes cluster. The control plane manages the entire lifecycle of workloads and the scheduling of resources in the cluster. So let's take a look at the components of the control plane, starting with etcd. So this is a distributed, highly available key value store that holds the state of the cluster. So etcd stores all the cluster's data, including configuration, current status, secrets, and the desired state of resources like pods, deployments, and nodes. So it's essentially the source of truth for the cluster. And an example would be if a pod is deleted, etcd still knows about the desired state, for example, the number of replicas, and the system can automatically recreate the pod. So now we have the Kube API Server, and this is the core communication hub of Kubernetes. The API Server is the central management point that receives requests from kubectl, APIs, or the dashboard, and it processes these requests, validates them, and updates the cluster's desired state in etcd. It also exposes the Kubernetes API to users and components in the cluster. An example would be if you want to deploy a pod, the API server processes that request and communicates with the rest of the control plane to make that happen. Next, we have the controller manager, and its role is to ensure the cluster always matches the desired state. So Kubernetes controllers are responsible for checking and ensuring that the actual state of the cluster matches the desired state. And if there's a discrepancy, for example, a pod crashes, the controller works to fix it by recreating the pod. So an example would be the replication controller, ensuring that the correct number of pod replicas are running as defined in your configuration. And next we have the scheduler, and its role is responsible for scheduling workloads, so pods, onto worker nodes. And when a new pod is created, the scheduler decides on which node the pod should run based on resource requirements, so CPU and memory, affinity rules, and resource availability across nodes. So an example of this would be the scheduler may decide that pod 1 should run on worker 1 because it has enough CPU and memory available. So now let's look at worker nodes. So we have worker 1 and worker 2 in this diagram. So these are the actual machines where the workloads, so the applications, run. So the worker nodes contain the components necessary to manage the execution of pods. And there's a couple components within each worker. So the kubelet is the agent running on each worker node. And its main function is it will communicate with the control plane, specifically the API server, to receive instructions like creating pods. It's responsible for ensuring the containers described in each pod are running and healthy on this worker node. So an example would be if the API server instructs the worker node to create a pod, the kubelet pulls the necessary container images and starts the containers. Next, we have the kube-proxy, and its main role is to handle network communication within and outside the cluster. So it will manage network rules and load balancing for the pods running on the worker node, and it ensures that traffic between pods, services, and external requests is routed correctly. So an example might be if a pod on worker 1 wants to communicate with a service running on worker 2, the kube-proxy will handle the routing of all that traffic. And we can get a little bit more granular looking at the pods. So a pod is defined as the smallest deployable unit in Kubernetes, and it encapsulates one or more containers that share the same network and storage. So pods are typically ephemeral and may contain multiple containers that need to work together. For example, a web server and a logging sidecar. And an example would be each worker node has multiple pods. A pod might contain multiple containers running different services or applications. And to get even more granular, we can look at the containers. So inside each pod, you see individual containers, container 1, container 2, container 3, etc. And containers run the actual applications. So for example, web servers or databases. And Kubernetes manages containers through pods as it's more efficient than managing the containers directly. So finally, let's look at the step-by-step flow and how everything works together. So first step is user interaction, right? So a user issues a command using kubectl or interacts with the dashboard, for example, to create a new pod. And then the second step is we have the Kube API Server. So the command is sent to the Kube API Server, which is the central point of communication in the control plane, and it processes the request and stores the desired state in etcd. For example, I want 3 pods running. And then the scheduler looks at the available worker nodes and selects one based on resource availability and scheduling rules. For instance, it might decide that worker 1 has enough CPU and memory to run the new pod. The controller checks that the desired state, for example, 3 pods running, matches the actual state. And if not, it instructs the system to create or terminate pods as needed. And we can think of step 3 as being this third section over here. So the kubelet on the worker node is the next component. So the kubelet on the chosen worker node, say worker 1, pulls the necessary container images from the registry, creates the containers inside a pod, and monitors their health. And then we have kube-proxy. So the kube-proxy configures the network on the worker node, and this enables communication between pods, services, and external traffic. And finally, we have pods actually running, right? So the container within the pods starts running and the application is now live.